Alright, in this video we're going to talk about double displacement reactions, and the double displacement reactions are also called precipitation reactions, and that's because they actually makes the precipitate. Another way of saying one of your products is actually going to be a solid. A very generic double displacement reaction is going to look like this. Assume I have A, B reacting with CD, and when it comes to predicting the product, and that's one of the questions you guys gonna have, you have to be able to predict the products of these reactions. And a simple way of predicting these double displacement reactions, you can say the inside stays inside and the outside stays outside, and I explain that in a bit. In this case, when the inside stays inside, I would say it's going to be the CB and it's going to be the AD. All right, now how does that really work? Let's kind of break it down. We have an AB as one of our ionic compound in the reactants, and the CD is going to be the other ionic compound in the reactants. So in an ionic compound, you mostly write your cation first and then your anion. So that means in AB, A is going to be your cation, and assume that's 1 plus charge, and B is going to be your anion, and assume that's a 1 minus charge. So these are hypothetical charges on those. And then in case of CD, you have a 1 plus charge, and then D is going to be 1 minus charge. Okay, well, when it comes down to predicting the product, figure out what this A1 plus can react with. Now your cations are always going to get combined with the anions, so you can easily see this A1 plus can only get combined with the D minus now. Okay, so that's why you make an AD there. And then this BC, it can only get combined with the C1 plus, so that's why you have a CB there. So that's how you predict the product, and that's how you're going to be doing in a real reaction. Well, the next question in these reactions is, what's really the driving force? So every single reaction usually have a driving force, and the driving force in these precipitation reactions is actually the formation of the solid or the precipitate. So one of the products that you actually be making is going to be the solid, and that could be either the CB or the AD, and I do not know that yet. That has to do with the solubility rules, but right now just know your driving force is the formation of the solid as one of your products. Okay, well, what does a solid really mean, and what else we have in these reactions? Now, in precipitation reactions, you will have two phases. One of them is the aqueous phase. Aqueous phases are the one that actually dissolves in water. And when they dissolve in water, they actually break into ions. And we'll talk about that in a little bit when we do the solubility rules, what that really means, breaking into ions. But right now, know that there is one phase to be aqueous that's going to be soluble in water, and the other phase is going to be the solid, and the solid is actually going to be insoluble in water, and you also call that precipitates. So formation of the solid is the driving force, and for the most part your reactants are actually going to be the aqueous. So I'll say the AB is an aqueous, and your CD is also an aqueous, and out of the CB and the AD, one of them would be a solid and the other one would be a aqueous. Okay, well, how do you really know which one is going to be the aqueous and which one is going to be the solid? That has to do with the solubility rules. So let's focus on the solubility rules of these ionic compounds. Your rule 1 says these are the compounds that are actually always going to be soluble in water. And these are the compounds of alkali metals. So if you see an alkali metal cation, so remember the alkali metal is going to be the Li1 plus, the Na1 plus, potassium 1 plus, you have rubidium 1 plus, cesium 1 plus, and then francium 1 plus. So anytime you see this cation, it does not matter what anion you have, they will be soluble in water. And along with these alkali metals, The other cation you have to worry about that's always going to be soluble in water is the ammonia. So it's going to be NH4, sorry, ammonium. That's going to be NH4 plus. Okay, so in addition to that, your in addition to cations, you do have some anions, and their compounds are always soluble as well. And the examples of those anions going to be the NO3, 1 minus, that's called the nitrates. So if you have a nitrate as an anion, it does not matter what cation you have, those compounds will dissolve in water. And the other example is the acetate, that's CH3COO 1 minus, and then the chlorate, ClO3 1 minus. So if you know your first rule, that covers almost 90% of the compounds that you're going to see in this chapter. The second rule is about the halogens. Now in the halogens, we focus on the chlorides. So you have a Cl1 minus. Change the color there. So you got the Cl1 minus in the chlorides and the bromide 1 minus, and you have the iodide 1 minus. Now, the compounds of chlorides, bromides, and iodides, they actually dissolve in water, except, so there is an exception, and the exception is when they are either bonded with the silver 1 plus, the mercury 1 plus, or the Pb 2 plus. So those are the three exceptions. So what that really means, if I have a compound that's PbCl2, that one is actually going to be a solid, so I'm going to write that down as an S there, not an aqueous. Any other compounds, any other cations you see with those halogens, they will be soluble in water. Okay, so moving along, when we look at this, the compounds of sulfates, the sulfates is SO4 2 minus. The sulfates are also soluble except, so the exception in the sulfates is going to be the same exception you have in the halogen and some other compounds along with it, some other cations along with it. So you have the Ag 1 plus, then you have the Hg 1 plus, you got the Pb 2 plus, and then you have a couple of other cations. That's going to be the calcium 2 plus, the strontium 2 plus, and the barium 2 plus. So those compounds are going to be insoluble. So for example, if I have a barium sulfate made in the products, that means that's going to be a solid. Okay, sorry about that. Okay, so then now we're moving on to the insoluble side. So these compounds of hydroxides are mostly insoluble. So the OH minuses are going to be insoluble except. So think about it. What could be the exception here? So remember, this is an anion here, OH1 minus, and we had said something about some of the cations in Rule 1, where we said if you have an alkali metal, cations or the ammonium, they will be soluble in water regardless of what type of anion you have. So the exception here is going to be the Rule 1 cation. All right, so the Rule 1 cations are going to be dissoluble, and the rest of them are going to be insoluble. And the other exception is the barium. So barium 2 plus is also going to be soluble for the hydroxides. So for example, if I have BaOH2, that will be actually going to be the aqueous, not the solid, because that will be soluble in water. Okay, so moving along, these compounds are phosphates. Remember, the phosphate is PO4 3 minus, the oxalate is C2O4 2 minus, your chromate is Cr2O4 2 minus, and your carbonates is CO3 2 minus. They are insoluble except, all right? So remember what the exception could be? It's going to be the Rule 1 cation. All right, so anytime they're bonded with Rule 1 cations, which are the alkali metals and ammonium, they will be soluble. If those cations are not there, if they're bonded with some other cations, then they will be insoluble in water. So those are your rules, and like I said, if you can get this rule 1 down, that covers a lot of elements. So rule 1 and 2, and then if you understand rule 1 and 2, then 4 and 5 is also going to be easier to understand. Okay, now let's be able to actually apply this in a real life, in a problem. A typical question involves writing a molecular equation which has to do with predicting the products and all that, ionic equation and the net ionic equation, and you eventually have to identify the spectator ions. And sometimes they just tell you what they will ask you what the spectator ion is going to be only. Okay, so assume I have this silver 1 nitrate and sodium chloride. So silver 1 nitrate means I have a 1 plus charge on the silver, and your nitrate is going to be NO3 1 minus. And on the other hand, I have sodium chloride, which is going to be Na 1 plus and Cl 1 minus. All right, so what I'm trying to do here is be able to figure out these formulas. Now keep in mind, sometimes the silver 1 nitrate would be written as only silver nitrate. That's because silver is always 1 plus, even though it's in a transition metal. Okay, so your compound is going to be the AgNO3. Okay, so I'm mixing that with NaCl. Okay, so now what's my product going to be? And what I had said earlier, your inside stays inside. So your sodium and the nitrate stays inside, and your silver and your chloride stays outside. So the outside stays with the outside. And then if you don't do it this way, you can go back to these cations and anions that you have written out and pair up the combination. So for example, in case of silver, what's the other anion it can pair up with? Now it cannot pair up with the NO3 1 minus because it was already in the reactant. So the only other anion it can pair up with is going to be the chloride. Okay, so you make that there. So that means we can see this a silver right there and this chloride right there. So those are the outside ions, so they stay together. So you will have, what's the formula going to be now? So Ag1 plus gets combined with Cl1 minus, so that's going to be AgCl, okay? And then, the other product going to be the Na gets combined with the NO3, and you can say the Na1 plus is combining with the NO3 1 minus, so I can say when I put them together, it's going to be plus NaNO3. Okay, so once you write down your products, you want to make sure you write down the phases of all of your reactants and the products. For the most part, your reactants going to be the aqueous phases, but let's just recall the solubility rules we just learned. Okay, so in case of silver nitrate, now nitrate is in the first rule, and what we have said about the nitrate, they are always going to be soluble regardless what cation they are with. So this nitrate, silver nitrate, is actually going to be the aqueous. So I'll write down AQ for that. Sodium chloride, so remember this got the sodium, that's in the first group ion, that's also going to be aqueous. And then silver chloride, let's come back to that in a minute, but then silver nitrates, or sodium nitrate, the sodium is in rule 1 and so is the nitrate, so that's also going to be the aqueous. Okay, well, let's look at the silver chloride here. In silver chloride, if I go back, I don't really have any rule for the silver, but we do have the rule for the halogen. And if I go back to the rule of halogen, and I know the halogens or the halides actually are soluble except when they're bonded with either silver, mercury, and lead. And that's exactly what we have in this case. We have this chloride bonded with the silver, so it's actually going to be a solid. So that's going to be the driving force in this particular case. Now, once you have predicted your product, you want to go back and make sure your reaction is balanced. All right, let's look at the silver. We have 1 silver on the reactant side. We have 1 silver on the product side, so that's fine. we got one sodium on both sides. Seems like this reaction is already balanced. If the reaction is not balanced, you want to make sure you balance it, and the reaction balance must be done after predicting the product. Don't balance the reactions before predicting the products. You must write down the products and their phases and then predict the reactant, balance the reaction. Okay, so this completed reaction is actually called the molecular equation. Okay, well, how about writing an ionic equation? So what happens in case of ionic equation, if you have anything that's aqueous in phase, you break that into ions. Okay, and if you have anything that's solid, you leave that as it is. So leave it as it is. So in this particular case, we can see the silver nitrate is an aqueous, so that's going to be Ag1 plus aqueous, so I'm breaking those down into the ions, plus NO3, 1 minus aqueous, plus Na plus aqueous, remember your NaCl is an aqueous as well, plus Cl minus aqueous, and that goes on to make AgCl, so you want to leave the AgCl as it is because that's your solid, plus the NaNO3 also gets broken, so it's going to be Na1 plus aqueous plus the NO3. I'll just write that down on the bottom here. That's going to be the aqueous as well. So this is going to be your ionic equation. All right, so that was your ionic equation where you break down all the aqueous into the ions and leave the solid as it is. Now, when it comes to writing the net ionic equation, which we're going to do now, in net ionic equation, you cancel out anything that's common. So if I go back and look at what are the common ions we have, the NO3 1 minus right there and the NO3 1 minus right there on both sides of the reaction, so they cancels out. And then in addition to that, we have Na1 plus on both sides of the reaction, so that also cancels out. Okay, so once you cancel out these common ions, now rewrite the reaction. When you're rewriting this reaction, it's going to be Ag1 plus aqueous plus Cl1 minus aqueous, and that's going to go ahead and make AgCl solid. So that's going to be your net ionic equation, and whatever ions cancels out, those are going to be called the spectators. So in this case, the spectator ions are going to be the sodium 1 plus and the NO3 1 minus. All right, hopefully this video was helpful, and I'll post another practice video.